All right. So first off, an apology. Apparently I set my office hours like 2 weeks ago, and I've been confused that no one's been coming. Apparently I never posted what room I'm in. So sorry. I was very confused on Thursday when no one came there on the day of the quiz. So I posted on Discord where my office is and updated the Piazza post. It's BA 5110, 5110. Again, didn't mean to do that. Someone actually told me at the quiz that they don't know where my office was. I'm like, well, check the post, and it doesn't have it there. So yikes. Quiz, we have a meeting with the TAs tonight. Hopefully it'll be graded sooner rather than later. So far the quiz average is like 83% or something. So hopefully it wasn't too bad to anyone, at least better than lab 1. So, but yeah, it's funny when we have this many students. You know the freebie question that was like, what course is this? Someone got that wrong. Oops. So hopefully that wasn't anyone here. But yeah, apparently if you have a class big enough, that happens. Control systems.
Are you serious?
Yeah. Yeah. Unfortunately, this course is not control systems. So if you're here, sorry, you didn't get the point for that one. All right, so today we'll be talking about semaphores, more fun synchronization primitives. So we saw locks before that ensure mutual exclusion so that, between a lock and an unlock call, we have a critical section, and we know only one thread can be there at a time. So if we have accesses to the same memory location, there can't be any data races because it needs 2 concurrent accesses. But it does not help ensuring ordering between threads, which is something we might want. So how do we ensure ordering between 2 threads? So let's look at our example and a few silly examples. So if I have this code where one thread, I have 2 threads, one thread runs print first, the other is print second, and then the question is how do I get one to always print before the other? So we know some way to do this already. Anyone think of some solution to do this? Yeah. Yeah, so one thing we could do is do cooperative threading. That would work. And then we could, actually that would not work because we'd have to make sure that the first thread always runs first. I guess if you control your scheduler too, you can schedule it first and then yield. So, but what's another way? Yeah. How would I use a lock? So where would I put it if I want to use a lock? So in the main, I'm just going to create 2 threads and then join them. So you want a lock around that? Like what? Like a lock, unlock, like that? Okay, so at least for that, so initially when we run this, only one thread's active because the process is created, only one thread's running main, in which case the lock and unlock would do nothing because there's only one thread doing this anyways. And then we create our 2 threads and then we're off to the races. So can I just reorder these to ensure that there's some order between them? So if thread 0 runs, yeah.
You join thread 0 first, then you create thread 1.
Yeah, so one thing I can do if I want to make sure they run in order is something like that. So I create the first thread that runs print first, I join on it, so I wait for it to finish, and then I create the other thread. But this definitely works, but that is not going to work super in general. If we wanted it to just do that line and then do the rest of the code in parallel, that wouldn't work because we're essentially serializing our program there. We could do it with the mutex too, and let's see a clever solution we could do for that, but it's like we're not going to use a mutex super effectively. So we could create a mutex, and remember initially it is in a unlock state, so which this looks kind of weird to unlock it, and then in the second thread we can lock it and then lock it again. So if this thread happens to get scheduled first, it'll call mutex lock and then try and call it again, which is kind of an error, but in this case it does work because it would wait for it to be unlocked again. And then the first thread could go ahead and come and unlock it, and then we could pass by this lock call. And that's like a super roundabout way of doing it and not really a way you should use mutexes, but that actually works. But it's kind of an unorthodox solution, and we can do a lot better. So what we want to do, so this is our problem again, and to illustrate as well, so printf is actually thread safe, because if we go ahead and break it up into something like this, where we just split our system call into, or split printf into 3 system calls. So like this is first, and then I'm going second. If we compile and we run safe print, we'll see it all in kind of a jumbled order. So it went thread 2, thread 1, thread 1, thread 2, thread 1, thread 1, or thread 1, then thread 2, right? It kind of got in a super jumble ordered. And every time I print it, it's going to look slightly different because they're just kind of racing at that point to see who can make the system call first. So in that case, we got I'm going second, and this is first, luckily, but then we run it again, and we get all sorts of different orders. All right. So printf is actually thread safe. You may need to ensure things like that. So if we wanted to make safe print essentially thread safe, we could put a mutex along, or we could put a mutex around all of those 3 write calls so they all happen at the same time, and you can't get interrupted by the other thread in the middle of it. So you can go ahead and do that for practice if you want. You just wrap a mutex around all the write calls. But the thing we're going to use is called a Semaphore, and they are used specifically for signaling, and unfortunately this is another overloaded word because it does not correspond to Unix signals at all. It's more like the actual English usage of the word where I want to tell you to do something. So Semaphores follow a few specific rules, really only 3 rules. So Semaphores have a value that's shared between threads. And optionally, you can use Semaphores as interprocess communication if you want to synchronize between 2 different processes as well. But that's an optional thing that we won't even get into in this course. But you can think of Semaphores as just having a value, and the value will always be 0 or greater. Then it only has 2 fundamental operations. So the only things you have to remember about Semaphore has a value and then 2 fundamental operations. Wait just decrements the value atomically, and if it can't go negative, it will sit there and wait for another thread to go ahead and post. And what post does is just increment it. So it just increments the value, wait decrements the value, and does not let it go negative. So wait does not return until the value is greater than 0. So if you call wait and the value is 0, sits there and waits and waits and waits for another thread to post it back up to 1, and then it can decrement it from 1 to a 0 and then actually return from the wait call. So the cool thing about Semaphores is you can set the value to whatever you want, and you can think of that by default. That's the number of wait calls that can pass without any calls to post. So if we want to use that, oh, sorry, I'll show the API of it looks like this. There's an include for Semaphore, and then it kind of looks like a mutex. It has an init and a destroy. So it takes an address of a Semaphore, which you can allocate however you want, put it on the stack, malloc it, do whatever. Then the second argument is p-shared, which just specifies whether or not you want this mutex to be shared across processes. So for the purposes of this course, we'll just always set it to 0. That says don't share it. And then there is the value. So that's the initial value that you create for the Semaphore. Then after you destroy it, and then there's our two fundamental operations, wait and post. And there's also a version of wait that doesn't sit there and block. So try wait will let you try and decrement it. If it can't decrement it, it will tell you. If it can decrement it, it will also tell you, so you know whether or not you essentially have decremented the Semaphore. And they're all atomic operations, so that's why you use Semaphores. They're all atomic. You won't have any data race problems between them because post and increment are atomic. All right, so if we go back to our problem to make one thread always print first, and just in the slide I removed the return statement, could we make a Semaphore to make sure that one prints before the other? Yeah.
Could you set the initial value to 1, and then in one of the, I don't know what the initial value would be, but like call wait post on maybe the first one, and then wait post on the second, but make sure that somehow the first one gets in first.
Somehow, all right, let's go through it. So let's just go ahead and we'll go ahead and include Semaphore. Let's just declare it on there. Make sure I don't do anything stupid. Defined but not used, okay. So we want to initialize the Semaphore. So sem init. I'll give the address of it. I'll say it's not shared, and then the initial value you want is 1.
Should it be 0? So the first one will increment it, and the second one will wait until the first one increments.
Okay, so generally it's easier to place our wait. So if we set the initial value to 0, whoops, it's called sem. If we set the initial value to 0, that means if something calls wait, it'll sit there and wait until it goes above 0, right? So it would just sit there and block. So it sounds like we should probably put the wait here, right? So if we put the wait here, right now how we have the code, so we set the initial value to 0, and now if this thread happens to get scheduled first, because again, we can't guarantee what order they run in, so we have to argue about both of them. If this thread gets scheduled first, it will hit sem wait. The value of the Semaphore is 0, so it will just sit there and wait for it to go above 1. So even if that thread gets scheduled, it just sits there at that wait call and can't do anything. So now if print first goes ahead and executes, it would print, and then it would finish, and then thread 2 is kind of stuck, right? So what are we missing? Yeah.
Miss a post after you print f first.
And we agree with that? Okay. So, oops, post. So if we have a post, then that should ensure us order, right? So if this thread gets scheduled first, the value of the Semaphore is initially 0, so it'll sit there and wait. Wait won't pass, won't do anything, like Monopoly Man won't pass go, doesn't collect $200. Then if whenever you schedule thread 1, it would print f and then print this as first, and only after it's done printing would it increment it, and then the value of the Semaphore would be 1, and then it would kill that thread, or it at least would become a zombie thread, but we don't have to care about that right now. And then thread 2 would get scheduled, and then the wait would actually return because it can decrement it from a 1 to a 0, and then it would print f, I'm going second. So if we compile that, we should see, again, it's not guaranteed that, if you run it 1,000 times and get the same answer, that there's no problem, but we argued about it, and if we run it a bunch of times, it actually does what we thought. All right, so we have ordering between our threads, and even if we could have code after the printf and after that printf so that they could actually run in parallel too. It's not like our join case where we just essentially make it sequential. It actually ensures some type of order. So that's pretty cool. Everyone get Semaphores? We can do all the hard questions now. All right, so let's do something harder. So again, this is just on the slide, so we always have print first, execute first, and then print second. So this is, again, just so you have it on the slides. So no matter what thread executes first, we get the same order if the value is initially 0, right? So assume this is just what we went through, right? So what happens if we initialize that value from 0 to 1? Looking at our code. Yeah. Yeah.
The second print is able to get past the wait because it's already 1, so it can decrement it. So it is scheduled first, and you can print first.
Yeah, so if the value is initially 1, now if print second gets scheduled first, it can actually go past the wait and decrement it from a 1 to a 0, and it just happily goes and prints. And then the first thread would go and post it from a 0 to a 1. And it doesn't matter. We'll just have a 1 as a value at the end of that program. And then, if thread first gets scheduled first, it would print and then increment. It would just post it from a 1 to a 2. And now print second might get scheduled, and then it would just decrement it from a 2 to a 1. So essentially, if Semaphores really, the initial value really matters when you want to prevent things, because we didn't change our post and wait calls at all. We just changed the initial value, and suddenly it essentially just doesn't do anything anymore, right? Yeah.
What about if you have a print third, then you want to make sure the orders are, and you want to set an order for that.
Yeah, so with Semaphores, even if there was a print third and we had a third thread, we could ensure ordering between them. But you might have to use 2 Semaphores to ensure order. Yeah.
Yeah, that's really my question. Can you say one and 2 threads? Or you need to make a new semaphore for every pair of threads with ensure ordering?
So if you want to ensure ordering for 3 threads, the easiest way is just to have 2 Semaphores, one that acts like this, and another one that essentially does the exact same thing. Yeah. Yeah, so you could just chain them. So we could have print third, and then it would have a post here to another Semaphore, and then a wait here. So that the only way to have the third thread run is for this thread to run, which needs to run that thread, and then it would chain down. So we could chain them as long as we want. We could ensure 4 threads order, or 4 threads go in the same order. We could just keep on chaining them. All right. So can we use a Semaphore as a mutex? And if so, how? Because they kind of look the same, right? Yep.
I mean, it's lock and unlock, basically. Because like when you post, you unlock the other thread.
Yeah.
And then the wait is just like lock if the semaphore is 0.
If the initial value is 0. Right. So if the initial value of the Semaphore is 0, and we use wait as lock and then post as unlock, it behaves exactly the same as a mutex, right? So a Semaphore is a more, it's a more general thing than a mutex. A mutex is actually kind of like a special case of this. But it can do more because the initial value doesn't have to be 0. It can be anything we want. But so if you want, you can go ahead and write that data race example we saw before. Instead of using a mutex, you could use a Semaphore. But again, it's kind of messier. The initial value would have to be 1, not 0. Because if it's 0, it would hit the wait, and then it wouldn't be able to decrement, right? So it would block immediately. So it's a mutex if the initial value is a 1, not a 0. So that way, one thread can go ahead, call wait, pass, and then post it back up from a 0 to a 1. So it's just going to constantly ping pong between 1 to 0 and then 0 to 1, right? So you can go ahead and rewrite that example if you want. But can we come up to a solution to a bigger problem? So this is for a producer and consumer. So assume you have a circular buffer where each slot is either empty or filled with some data. We don't really care what it is right now. And then the producer should be the only one to write to the buffer if only the buffer is not full. And the consumer should read from the buffer as long as the buffer is not empty. And then all consumers will just share an index and all producers will share an index, and then initially they are 0 and the buffer is completely empty. So at the beginning of time, both the producer and the consumer threads as a group would all be pointing to the first index, and it's essentially just going to, and it's empty, so it's going to wait for the producer to start filling some slots, and then the consumer can come in and pull the data out of the slots and actually use them. So let's look at the code for that because it is much more involved. So at the basic level, let's see. Yeah, so at the basic level, this is our producer thread. So I'm just going to use a Semaphore to keep track of the number of elements I'm producing and consuming. So that's just for some accounting stuff. You could imagine it would be more involved if you're actually doing this, or you just loop infinitely or something like that. But in my code, I'm just going to sleep to simulate doing some work, and then I'm going to fill a slot, right? And initially, it'd be wanting to fill slot 0, and then go through and wait until it's full. And then in the consumer, it's exactly the same thing, but it's going to empty a slot instead of fill it, and then it's going to simulate doing some work to go ahead and consume that data. So if we go ahead and run this, producer, consumer, so even if we do that, so this is the, what did I say? So the number of producer threads and then the number of consumer threads. So if I run that, I'm going to produce 15 things, and my buffer size is going to be 10, and they take some time. So if I run that, I see that there's a lot of conflicts, so I'm just printing out a red message any time that essentially I detect a data race. So initially, I have a bunch of producers and consumers, and I don't have any ordering between them right. So immediately it's trying to empty slot 0, which initially it doesn't have any data in it. So that's an error. So the slot's already empty. I shouldn't have done that. And then it would fill slot 0 after that. So I probably should have waited like a little bit for that to happen. Then again, it does the same thing where it empties slot 1 but right before it fills slot 1. And it does that over and over again. And then eventually it catches up because it just happens to fill slots a bit faster. And then it starts emptying them, and we have no issues here until essentially it wraps around, and then it fills slot 0 again because it wrapped around, and it hasn't emptied slot 0 yet. So it just kind of overwrote something that hasn't been actually handled yet. So it's already filled, and we write over it a few times, and then we end. So we kind of screwed up a lot of times there. So how would we try to ensure some type of ordering between these threads? Yeah.
You said that producer fills faster than the consumer consumes, right?
Let's see, what takes long? Yeah, so the producer takes only 100 milliseconds, and the consumer takes 120 milliseconds.
And then you just kind of go in a circle while the consumer throws down the producer.
Yeah. All right, so how would I fix my issue? Yeah.
You always want to produce first before you consume, so you might put wait for consumer and post after producer.
Okay, so what do we want to do? We want to make sure that slots are actually filled, or you never overwrite filled slots. Okay, well, let's make sure yeah.
I mean, I think for the consumer, you just check if the slot is empty, and then never mind.
Check if the slot is empty. Yeah, well, we learned Semaphore, so let's try and use the Semaphore for it. So let's try and keep track of, let's see, the number of empty slots. So we'll have a Semaphore that represents the number of empty slots. So one of the first questions is going to be what we initialize it to. So I'll just put that as a 0 for now. So what thread needs to wait for empty slots? Yeah, so the producer should wait for empty slots, right? So if I want to wait for empty slots, the easiest thing to do is put my semaphore wait here, empty. Yeah.
What's a try wait?
So try wait is, instead of just waiting and it blocking there, it's kind of like try lock. So it will try and decrement it and then tell you whether or not it did it. So that's why I have it. So I just have a Semaphore just to see how many times the loop runs for. So I just essentially say how many elements I want to produce and just decrement it every time until it's eventually 0. So, but that Semaphore is unrelated to actually ensuring some type of ordering. All right, so I'm going to wait for some empty slots. So if I'm waiting for an empty slot, what creates an empty slot? Yeah. Yeah, the consumer, after it empties the slot, I should probably post, right? Okay. So if I have that, then I'm a bit closer, but the question is, what should my initial value be? Because if I run this, producer consumer with say 4, some bad things happen. Right, so slot's already empty, which is okay because I'm just trying to get rid of the error where I'm filling a slot that's already filled. So in this case, I fill some slots, slot is already empty, that's okay. And it seems like I did it, but there's still an issue here. So should the initial value here be 0? So in this case, what thread ran first and what will always run first in this case?
Empty will always run first.
Yeah, so which is the consumer, right? Yeah, so in which case here, because I have a wait here and my initial value is 0, if a producer happened to get scheduled first, it would just sit there and wait, right? Even though all the slots are already empty. So I should probably change that because it's going to wait for it to empty slots and post up every single time. And it's kind of also weird because it would go from, it initially has, how many slots are initially empty? All of them, right? Which is whatever my buffer size is. So that would just increment this up to buffer size and then start running the producer, which would pretty much always guarantee some type of data race. So I should probably just change this to set my initial value as buffer size. Oops, and I misspelled it. All right, well, that's one side of the equation. So what's the other side? Probably keeping track of the number of filled slots, right? So let's go ahead and do that. So we'll have another semaphore for filled slots. And it's probably easiest to place our wait. So where do we want to wait to see if we have any filled slots available? Yeah, right before we empty it, right? So sem wait. We want to make sure that there's at least a filled slot in order to empty it. And then what's the thing that fills a slot? The consumer here, right? So sem post filled slots. And then the last question we have to answer is what should our initial value be? 0, right? Because initially there are 0 filled slots. Filled slots. Whoops, 0. So if we do that and say the producer gets scheduled, gets scheduled 10 times in a row, it would go ahead and since empty slots is 0, it would it would wait for empty slots, and initially empty slots is the size of the buffer. So it could allow 10, whatever the size of the buffer is, producers all at once. So all 10 could be there. 10 could pass the wait call and fill, which is fine. We just don't want to overwrite any data. So we don't want 11 because they would obviously have to share the same slot and probably overwrite each other. So even if only the producer was scheduled, it would be able to go through and fill up every single slot. So it would fill up every slot and then post the number of filled slots, which might go all the way up to the size of the buffer, right? And then in the consumer, it's just going to wait for filled slots. So if it happens to get scheduled first, because filled slots is initially 0, it's going to sit there and wait finally, right? So it's not going to be able to do anything until it's at least filled one slot up, and then it would go ahead and empty it, and then post up that there is an empty slot so that the producer could go ahead and fill that again, right? Any questions about that? Hopefully it works if we compile it. Oh, I already compiled it. So if I do that, right, I can start any number of threads. I'll do 4, 4. So there we go. I don't have any data races in this case. You can verify what happened. So it filled slot 0 first, emptied slot 0, then it filled 3 slots in a row. Again, we don't get to control what gets scheduled at what time. Then it empties slots, which have been filled, and happens to do 3 of them. Fills slots all the way up to 7. Empty slots, it would have to only be up to 7. Then fills slots 8, 9, 10, and it can actually wrap around now because it's already emptied slot 0 and 1. So it can go ahead, fill those slots. It still has room. Then it goes ahead, empties some more. Right, then fill slots all the way up to 4, and then empty slots all the way up to 4. And we're done. No data races whatsoever. We're good, right? All right, any questions about that? Yep.
So if they didn't both start at the same index, would this still work?
If they do,
So if the producer and the consumer started at different slots.
yeah, so if they start at different slots, this wouldn't work because we'd have to keep track of what slots. So this only works because they start at the same slot and they go around together, right? Otherwise, we'd have to do something a bit more involved. Okay, well, additional question then. So I can have multiple producer and consumer threads, and they're all and the producer has an index, the consumer has an index, and they're probably shared between threads. So what likely is going to happen in fill slot or empty slot that I nicely did for you? So is there potential of a data race in there? Yeah, so, well, if all producers share the same index and they essentially fill slot's going to at least increment it, right? Change the index to the next one. That's a data race that we already saw before. It's exactly the same as the plus plus count. So in there, one of the things we can guess is that it should probably look like this, where it has the easiest thing to do to prevent a data race is to just throw a mutex around the whole thing. So I get a mutex, I just call it mutex, I lock it, and then within fill slot, I go ahead and access my buffer. So I'm modifying my buffer. So not only are all the producers, sharing an index, all producers and consumer threads have to share the same buffer, right? So I have to protect all the reads and writes to there. So in here, I just put a mutex around the whole thing, and then I, fill the buffer and then increment the producer index and set it to fill, and then here I just wrap it around in case. So because we are sharing the buffer, we also have to put a lock around empty slot as well. So it would have a lock and an unlock around the whole thing so that I prevent data races. Yeah?
Is this for when you have multiple producers or multiple
Yes.
Then, is it possible that like only one of them can pass semaphore, but because it's not possible.
Yeah, so I wouldn't need to get as involved if I only had one producer thread and one consumer thread, because the only thing modifying the consumer index or the producer index would only be one thread. If I only have one thread modifying it, I don't have a data race, so I wouldn't need to protect that. I would probably still have to protect writes to the buffer though. Yeah.
Wait, so the consumers and producers are different threads, right?
Yep.
How about like what if a producer writes and then consumer reads the previous value? Like, is there a lock for that? Like, is
Reason-
there a race for producer and a consumer, the same slot?
Yeah, well, so initially it's slot 0, right? And they're all empty.
Right.
So what happens if, let's scroll back up, fill slot. So initially they're both empty, right? Or they're all empty. So what happens if the producer gets scheduled first? That's fine, right? It can fill in that slot because it's empty. But if the consumer gets scheduled first, right, initially the number of filled slots is 0, so it would sit there and wait. So for the first element, the first thing we know that has to happen to it is it has to get filled because it's initially empty, right?
Yeah, no, that part I get. I'm talking about like data race when you're writing to the buffer.
Oh, yeah.
So
So
between a consumer and a producer, did you put a?
yeah.
Do they never like read and write at the same time?
No, so there is potential of a data race for that buffer, but in empty slot and fill slot, that's the only place I modify the buffer, and both of them have a mutex around the whole thing.
So the mutex means no two threads can execute that block of code at the same time.
Yeah, any of the blocks of code at the same time.
Also,
So I have one mutex, and I have a lock unlock call around fill slot.
so that means that all the other threads are blocked.
Yeah, and I have a lock unlock call around empty thread. So because of that, I know that at one specific time, either one thread's going to be in this critical section or the other, and not both. Because in mutex, remember, if I just have lock, it means that only one thread is allowed, after the lock at any one time.
Yeah, but after just that lock, right? Not in the entire executable.
Yeah, but they're sharing the same lock, right? So either empty slot gets called first, and that lock passes, and then all this is, that's the only thread that's executing this. Because if this thread was in the middle of empty slot, and then say another thread comes in and calls fill slot, well, the other one already has the lock, so it would just hit the lock call and sit there and wait. Right, so I have two critical sections here, but only one thread can be in either of them at one particular time. So that's another way for the lock. So you can have multiple critical sections with the same lock and know that only one thread will be in one of those at any given time. All right, any questions about our producer consumer? It's kind of cool. All right. So on the slides, there's just solving problem to first ensure that producers never overwrite filled slots and that consumers never consume empty slots. So that's just what we did. So here was our final solution to ensure proper order for producers and consumers. And again, really depends on the initial value to get this actually correct. So what happens if we initialize both Semaphores to 0? Then if we initialize both of them to 0, what's going to happen?
It will not run.
Yeah, it's just not going to run, right? So if they're both initialized to 0, the first thing that both the presumer and the consumer does is wait. And if the value is 0, it's not going to pass wait. So no matter what gets scheduled first, either one's going to wait or the other's going to wait, and doesn't matter how many threads there are, nothing will ever call post. So it'll essentially just sit here and think about the poor decisions it made, right? All right, so we use semaphores to ensure some proper order. They contain an initial value that you choose. They essentially just have two operations, increment, which is called post, and decrement, which is called wait. And it blocks if the current value is 0. That's the only difference for wait. And then you still need to prevent data races because this is only ensuring ordering. You still have to identify data races, and they're the bane of your existence. Okay, so let's go over some question for that set context thing that is in lab 2. So has anyone looked at this before? Hopefully this is new. So this is a question from a midterm, and Ashwin went over it, and it's probably a good thing to go over. Hopefully it helps a bit with lab 2. So you know that implementing thread switching is a little tricky. To simplify matters, you start by implementing thread switching between just 2 threads. A and B, as shown below. You have added A and B to the run queue and initialize their thread context, so they start executing thread A and thread B at this, when they're run for the first time. Your scheduler happens to run thread A first. So we have 2 that are initialized. Thread A wants to start running there. Thread B wants to start running here, and we're supposed to say, circle the output you expect to see, and we have a whole bunch of different options. So let's see what the output should actually be. So we're going to run thread A first, so let's put active threads in blue. So we want to start executing first, and thread A is going to go first. And first thing it's going to do is declare a B on the stack, and then set its value to 1 or 0. So its value of D is 0 after that line. Then it's going to go ahead, go into the while loop. So I is a global variable up there, and it's set to 0. And because it's a global, it's going to be shared between threads. So first it comes in the while loop because I is less than 3. Would do plus plus I. So we're going to update that value of I from 0 to a 1. And then it's going to go ahead and print FA, whatever the value of I is. So it's going to print off A1 first, right? Everyone agree with that? Then after that, it sets D equal to 0 again. Then it sets get context for thread A. So next time you set or call set context on thread A, it's going to resume there. So let's put a little placeholder there. So this is where thread A would resume if we called set context on it again. So then it would go into this if D is 0, so then it would update D to be a 1. And again, it's on its stack. So we'll go ahead and update that from a 0, that was a big eraser, to a 1. And then it's going to call set context on, then it's going to call set context for thread, for thread B. So thread B is just going to start executing, become active. So this is the state of thread A's stack when we left it off. So let's go ahead and just mark it down as what the value of D is. So whenever something calls set context of that, we know what D is. So thread B is going now. So we'll change that to blue, and now we're thread B. So it goes ahead, declares a B on its own, or D on its own stack, and sets its value to 1. And then it would come into the while loop. So I is 1, so that's less than 3. So it would come in here and then increment I. So now at this point, I is not 1, it is 2. And then next thing it's going to call printf D, what's the value of I? Well, it should be a 1 or 2. All right, everyone with me so far? All right, so then it updates D from a 1 to a 1, wow, and then it calls get context on B. So if B resumes, it's going to resume at that point. So I'll put a green marker down for that. Thread B would resume here. So now it goes, checks this if statement. If D is 1, it's 1, and then D is equal to 0. So we would go ahead and update D on its stack is now a 0, right? And then it would call set context and start resuming thread A again. So we'll just mark off what D is when it switched over. D was equal to 0. So we're back here for thread A, and D was 1. So now we're executing thread A again. So now if we check that if D is not 0, because it set it before and it switched back, but remember its stack is private, so it didn't change. So we're going to not evaluate that if to true, and we're going to go here, and then we're going to go up, check the while loop again. Is I less than 3? Yes, it's still 2. That's our global. Then we would do plus plus I. So I goes from a 2 to a 3, and it prints off a 3, right? And then it would go here, set D equals to, set D equal to 0. Call set context again. So at this point, we'll put a little marker just in case. So thread A would resume there. Then it would go into this if statement because we're still executing that blue one. It would set D equals to 1 and call set context. So it is now, the value of D is 1, and we're now going to move over to thread B. So let's change it back to be blue. So it's going to go check if D is equal to 1. It's not, it's 0. It would go fall through here, then go back up to here while I is less than 3. Current value of I is 3, so it would just boop, and then it would exit, and then it's done, and that's it. So we got A1, B2, A3, and hopefully that's one of the answers. It's the last one. Sweet. Yeah.
Why do we always assume A starts first?
Because it said the scheduler runs A first. Yeah. All right. Any questions about that? That's how kind of set context and get context work. All right. Sweet. We got 2 minutes early. Just remember, I'm pulling for you. We're all in this together. Whoops, and I dropped.